So let us start the second part of this lecture on adjoint operators and more properties of adjoint operators. We have the following theorem. Let x and y be two normed vector spaces let A be a bounded linear operator from x into y. Then we have R, the range of A star equal to X star, meaning that A star is surjective if and only if A inverse from the range of A into X exists and is bounded. Okay, proof. First, let us assume that R of A star equal X star. Then we know that N of A star, then the null space of A star is going to be equal to, I'm sorry, not of A star, because we want to go to the relation. Remember, the null space of the adjoint is related to the range of A, and in other words, you have to switch from A to A star. So if I want to have from the range of A star, I have to go to the null space of A. So this gives me the range of A star of the row down to the space, which is X star down to X, which is 0. Okay? And therefore A is injective. So this tells us, of course, that that A inverse from the range of A into X does exist. Okay? That's first part. Second part, let us look at that A inverse is indeed continuousness. Let us prove that A inverse is continuous or bounded. Okay? Let yn in R of A such that yn goes to 0. Okay? So, well, in other words, we are trying to prove that A inverse continues at 0. Let us prove, that A inverse of yn goes to 0. Assume not. Okay? And so A inverse yn do not go to 0. Okay? And even if we have to go to a subsequence, the problem is still invariant because subsequence of yn will still go to 0. And I can say that I can assume without loss of any generality, we can assume that delta equal the infimum of the norm of A inverse of yn's is positive. In other words, they are all away from 0. Okay? Great. So now set x equal a inverse of yn. Okay? So we have norm of, I'm sorry, it's xn greater than delta, and the norm of a of xn, which is yn, goes to 0. Okay? Set zn to be 1 over alpha n norm of xn times xn, where alpha n is equal to square root norm of a of xn over the norm of xn. Okay? Now, since norm of a of xn is less or equal, over the norm of xn. So we know that norm of xn is bigger than delta, so 1 over norm of xn is less or equal than 1 over delta. Norm of a of xn. So this will tell us that limit of alpha n when n goes to infinity is equal to 0, because the norm of a of xn goes to 0. Excellent. Now, if we take the norm of Zn, but the norm of Zn is equal to 1 over alpha n norm of a of xn over the norm of xn, and this is equal to alpha n squared over alpha n, and that's alpha n, meaning that the limit of the norm of Zn is equal to infinity when n goes to infinity. This is, I'm sorry, let's go back. This is a of Zn, sorry. Let's just, okay. This is a of Zn, because Zn is equal to, see, Zn is equal to 1 over alpha n norm of xn, this is Zn. So a of Zn will be here a of xn, and that's why we have this. So this is true with a of Zn. A of Zn norm, and this is not infinity, it is 0, because alpha n goes to 0. But, and, now if we take limit of norm of Zn is equal to limit when n goes to infinity of 1 over alpha n, because the norm, because we're going to have norm of xn over xn. Okay? So that's 1. And 1 over alpha n goes to 1 over 0, which is infinity. So the Zns are unbounded. Okay? But the limit of a of Zn is equal to what? To 0. Great. Let y star belongs to capital Y star. Okay? Then y star of a of Zn goes to 0 as n goes to infinity, because in norm they converge to 0, therefore they go to 0. So a star of y star of Zn goes to 0 as n goes to infinity, which tells us that for any x star in the range of a star, we have x star of Zn, which goes to 0 as n goes to infinity. But our assumption, since the range a star is exactly x star, so we get that Zn converges weakly to 0. And we know also that weakly convergence sequence is bounded. So Zn must be bounded. Contradiction. Limit of the norm of Zn equals infinity when n goes to infinity. So we have, so this is the desired contradiction, and therefore our assumption is that A inverse is continuous at 0. So A inverse is a bounded operator from R of A into X. That's the proof of the first part. Conversely now, let's take the converse now. Okay? Let us prove the converse. Let us prove the converse. Okay? So meaning, assume if A inverse goes from R of A to X exists and bounded. So we are assuming that not only the inverse exists, but it's also bounded. Let us prove that R of A star is equal to X star. Okay? Note, now from the properties we saw in the part 1 of the fundamental theorem that gives you all the properties of the null spaces and the ranges of A and A star, the relationship between them, we know that R of A star, the last part, is equal, to the null space of A sorry. It's equal to R of A star orthogonal, and this is equal to R of A stars orthogonal, that's N of A, the null space of A, that's property number 2, orthogonal. But since A inverse exists, means A is injective, so this is just 0 orthogonal, and that is X star. So we know that the closure of the range of A star is going to be X star, the dual of X. So what we want to prove now, we want to prove that, basically, let us prove that R of A star is closed. Okay? So let X star belongs to R of A star closure. then there exists a sequence xn star in the range of A star such that limit xn star equals to x star when A goes to infinity. Okay? By definition of the range, so for every n, there exists y star n in y star such that A star of y n star equals xn star. Okay? Which is equivalent to say that y n star composed with A gives me xn star. And now since A is invertible, okay, so we can say this is exactly xn star composed with A inverse. Okay? Now, since A star inverse is bounded, okay, we get that yn star minus x star composed with A inverse, okay, equal to xn star composed with A inverse minus x star composed with A inverse, and this is less or equal to the norm of xn star minus x star times the norm of A inverse. Okay? Since the xn star goes to x, this implies, so limit of yn star is equal to x star composed with A inverse equals to y star, belongs to y star, when n goes to infinity. Again, same calculations, this would imply, which will apply as above, will apply that in fact x star is equal to A star of y star, which means that our point x star belongs to the range of A star, and that is exactly what we wanted to show. Okay? Next result, continuity of this theorem. Let X be a normed vector space. Okay. Assume let X be a norm. Let X and Y. Sorry. In fact, no. Let X be a Banach space. Let's assume that X is a Banach space. Banach vector space. Okay. And let Y be a normed vector space. Okay. Let A be a bounded linear operator from X into Y. Okay. If A adjoint going from Y star to X star has a continuous inverse, then A has also a continuous inverse. So remember, we have shown that if A has a continuous inverse, say this is the converse of that one, then A star has an inverse, and there is that relation between the adjoint of A inverse is the adjoint of the inverse of A. But in this case, if you want the converse of that, you need to assume that X is a Banach space, okay? So here, proof. Okay, if A star has a continuous inverse, then A double star, the conjugate of the conjugate, has a continuous inverse. So for every X double star in X double star, there exists for every X star, we have M, the norm of X double star is less or equal than the norm of A star of X double star less M norm of X double star. And this is where M and capital M are constant independent of X double star, okay? Are independent of X double star. Okay, this is true for any X double star, any element in this. So now, let X belongs to capital X, and look at capital X as subspace of X double star. So we know that A double star of X is going to be exactly A of X, okay? And we get here that M, the norm of X, is less or equal than A of X, norm, less or equal than M, norm, X. See, for every X. So this implies that A inverse exists. A is one-to-one injective. So A inverse, so A inverse going from R of A into X exists. Okay? And bounded, in fact. And bounded. Not only it exists, but it is bounded by 1 over n, the little n. Okay? So it is continuous. Great. Next, we know that R of A, because X is a Banach space, R of A is closed. Okay? Okay, good. So we have R of A equal R of A bar equal to the null space of A star orthogonal. These are the properties between the two spaces, the last term of part 1 that we saw. And since A star is an injective, this is 0 orthogonal, and that is X. So in other words, our inverse here, so A inverse, not only defined from R of A into Y, into Y, but A inverse, what am I saying? This is X. Okay? So, Y. So in fact, A is surjective, so it goes from Y into X. In other words, that A inverse belongs to B of Y X. So is not just it exists on the entire space, and the image is. So here, the next theorem. Let's now assume both are Banach spaces. Let A be a bounded operator. Okay. Assume R of A is closed in Y. Then R of A star is equal to N of A orthogonal. Proof. We know that R of A star closure is equal, that was the third part of the orthogonal. Okay, so what we need to show, we just need to show that R, let us prove that R of A star is closed. Okay, if that's the case, then we get our equation that we are looking for. So the proof is very interesting because it's going to use an argument that we have seen before about how to generate a bijection from any bounded operator. So we need to remove the null space of A to end up with the injective linear operator, and to do that we use quotient spaces. Okay, so let's see. This is a very beautiful proof, very constructive, and very interesting. Okay, so here let x0 star belongs to R of A star closure, and let us prove that in fact it belongs to R of A star. So x0 star belongs to N of A orthogonal. Okay, so x0 star over N of A is equal to 0 over the entire subspace N of A. And now this tells us what? That whenever A of x equals 0, so that means that x belongs to the null space of A, then x0 star of x equal to 0. Very interesting. Okay? Wonderful. Particular, if A of x equals to A of z, then x0 star of x is equal to x star of z. Why? Because x minus z will be in the null space of A, and therefore x0 star of x minus z will be equal to 0, and that gives us what we want. Okay? So here, if we take now the class of x, okay, so in particular, if we take the quotient space, consider the quotient space x divided by n of A. Remember that A is continuous, therefore the null space is closed, and therefore we can use the quotient space. So this quotient space with the quotient norm is a Banach space. Okay, is a Banach space because we assume that X is a Banach space. Is a Banach space for the quotient norm. Okay, great. So now we take the operator as we did once before between quotient into out of A. Okay. So if you take x here, the class of x, we take A of x. So one will argue that what about the representative little x there? What if I take another one? That's fine, because if, note, if y belongs to the class of x, then x minus y belongs to n of A, which implies, which implies in fact that A of x minus y equals 0, or A of x equals A of y. So you see this function is, this operator A hat is very well defined, okay? And what's interesting, we have done this before, so I'm not going to do it here. We have, okay, that the null space of A hat, okay, is 0. 0 in the quotient space, which is, by the way, n of A. So A hat is injective, okay? Not only that, and we have that the range of A hat is exactly the range of A. So this operator A hat gives us an isomorphic map between R of A and X quotient N of A. Okay? So here A hat is an isomorphism, a bijection. Okay? And in fact, since everything is closed, we get that so R of A is closed, just a correction here, because we assumed it's closed. So R of A is closed, X cross N of A is closed, R of A is closed in a Banach space Y, so it is a Banach. Everything is Banach here, so we get that A inverse through the closed graph theorem, both, in fact, everything here, A hat inverse, sorry, A hat inverse, which goes from R of A into X quotient N of A is bounded operator, okay, as well as A hat, by the way. Okay, great. So now let y0 star, okay, belongs to the dual of R of A, okay, such that y0 star of y for any y is equal to x0 star of x, where for any y in R of A, for any y in R of A, and A of x equal y. So remember, this y0 star belongs to the dual of R of A. So it takes value, the initial values are in R of A, and its target set is R. Okay, so it's a linear function. But when you take any element in R of A, it has the form A of x. So remember our x0 star at the beginning. So we have now, so question is this x0 star of x, does it depend on x, or is independent of x? It depends only on little y, and that's why this y0 star will be well defined. Okay, so assume, so let us check it. Assume we have A of z equals to y, another one. So we have A of x equal A of z, and we have seen, because x0 star is equal to 0 in the null space, so we have x0 star of x equal x0 star of z, and therefore this y0 star is very well defined. So it is, and because everything is continuous, we can easily see that y0 star is continuous. Okay, so this tells us that Anbanach before we get there, let us see how we have that control over the norm. Huh? So note, we have a of x. In fact, we have for any uh, z, for any z which belongs to the class of x now, we have a of z equals y. So a hat of the class, sorry, not a inverse, a hat, by definition, a hat of class of x is equal to y. Or that class of x is equal to a hat inverse of y. Since a hat inverse is bounded, we get the norm of the class of x in the quotient space. This is less or equal the norm of a hat inverse times the norm of y. On the other hand, we had y star, y0 star of y by definition equals x0 star of z for any z in the class of x. Okay? So, absolute value of y0 star of y is going to be less or equal than the norm of x0 star, norm of z, and this is for any z in the class. So if we take the infimum, okay, so we are going to find that this is less than the norm of x0 star, the infimum of the norm of z, and that is the norm of x0 star. This is just the norm of the class of x in the quotient space, and we just proved that this is less than the norm of x0 star, the norm of a hat inverse, norm of y. So this y0, okay, so y0 star is continuous, bounded, and its norm is less than the norm of x0 star, the norm of a inverse, a hat inverse. Okay, so it is in the dual space of Ra, and since it is in the dual space of Ra, we can extend it, so Anbanach allows y0 star to be extended to y star, to be extended to y star, to be extended to y star. Okay, denote y0 star to be that extension, to be that extension. Okay, so we have now for every x, okay, so let x be in x, so we have A star, okay, the conjugate of, because it goes from Y star to X star, of that element in, okay, at X. So now let me just say that this one here belongs to Y star, and this one here belongs to X star. So that's why we can take this vector at X, this function at X, this is now Y0 star composed with A at X, and that is Y0 bar star of A of X. And now this vector A of X is in the range, and when we go down to the range, this is just Y0 because it's an extension of that one. Okay? And this is equal to, by definition, X0 star of X. So since this is true for every X in X, these two functions are the same. So A star of Y0 star equal to X0 star. In other words, as we wanted, X0 star belongs to the range A star, and this shows that R A star is closed. The next result is a beautiful application of all what we learned so far to the existence, stability, and uniqueness of the solutions of some linear equations. Applications. Let X and Y be two Banach spaces. Let A be a bounded operator, and we consider the linear equation A of X equals Y. So we are given little y in capital Y, and we are looking for X in capital X. So we're trying to solve it. Okay? So first of all, in order for us to have a solution, our Y has to be in the range of A. That will prove us the existence. We need to have Y in the range of A. Then we would like to know the existence, and we know that uniqueness, for example, not the existence, the uniqueness, has to do with, in general, for any Y, so it has to do with A being what? Injective. So if A has a null space equal to 0, then we have uniqueness. But sometimes it depends on the little y. Okay, so here let's look at exactly some of the conditions. Number one, assume the following. Number one, that R of A is closed. Number two, that Y star of Y is equal to 0 for any Y star in the null space of A star. Okay? So then, okay, just look what's going on. Okay, so this will tell us that, so, condition 2 implies that Y belongs to N A star orthogonal. But this one but the null space of A star orthogonal, okay, this is just the range of A orthogonal, which is the closure of the range of A. So our Y belongs to the closure of R of A, but we assume in one that R of A is closed, since R of A is closed, then Y belongs to R of A, okay? Because it belongs to this one, and this one is this one, and that one is R of A, and therefore Y belongs to R of A. And this gives us what? The existence. So X solution exists. Okay, which we claim that we have existence if and only if Y belongs to the range of A. Perfect. Next, we assume that A is bounded, since A is bounded, so it is continuous. N of A is closed, and we are gonna again is closed. Use A hat from X, the quotient space of N of A, as we did in the previous theorem, to R of A. Okay, so we know, and we have seen that A inverse is continuous. Okay, so A hat inverse exists and is bounded. That's what we just proved before. Okay, so what does it tell us? It tells us that, particularly, so that for every x in X, it tells us that the norm of the class of X, okay, in the X n of A quotient space, this is less than the norm of A hat inverse, norm of Y, where A of the class of X is equal what? To Y. So whenever we have that, then we have this inequality. Okay? So assume Y is not equal to 0. Okay? Then in this case, and epsilon, let epsilon be positive. Then there exists X epsilon in the class of X, such that the norm of X epsilon is going to be less than norm of X plus something, because this is the infimum, epsilon norm of Y. Okay? And this tells us that the norm of X epsilon is less or equal than the norm of A hat inverse plus epsilon times the norms of Y. Okay? Excellent. But now we know that X epsilon minus X belongs to N of A. Okay? So the norm of X is going to be less than the norm of A hat inverse plus epsilon times norm of Y plus the norm X minus X epsilon. Okay? So what happened in fact here, conclusion. By the way, note that, that if Y is equal to 0, okay, so if Y is equal to 0, then in this case, we can take X being in the null space, and we can take here this inequality. So the conclusion here, let me write the conclusion, and you will see that it doesn't matter whether y is equal to 0 or not. So here, the conclusion is that there exists C, there exists constant, C positive, such that, okay, for that y, there exists an x, for the y which satisfies the property number 2, okay, there exists a solution, exists x in x, and x0 in the null space of A, such that the norm of x is less or equal than C norm of y plus the norm of x0. So if y is equal to 0, x belongs to the null space, so this inequality is still valid. That's why it doesn't matter whether y is equal to 0 or not equal to 0. Okay? So it's really a beautiful property here. It's like we don't have only the existence, but also a control over that solution x. Okay, we can control it by the norm of y. So next we discuss, as we did with the Van Neumann operators, let's discuss some of the last properties in this adjoint business theorem. So from now on, we consider that X be a normed vector space, normed vector space. Okay. Let A be a compact operator, Okay. Let lambda different from 0. Set A lambda to be lambda I minus A, and then we take the adjoint and A lambda star equal lambda I star. This is the identity of X star minus A star. So remember that if A is compact, A star is also compact. Okay, and we have seen some beautiful properties, like, for example, for any n greater than 1, we have A lambda n, we have seen this, equals lambda n times I minus an, okay, and this will imply that the conjugate is going to be lambda n I star minus an star. And what's interesting is that we have seen that an is compact, okay, which implies that A sub n star is also compact. Okay, great. Let us show now, we have a beautiful theorem. Under the above assumptions, meaning that A is compact from X into X, and X is a normed vector space, then N, the null space, A lambda R, and the null space of its conjugate have the same dimension. Beautiful. They are finitely, because A is compact, so they have a finite dimension, right? Both of them, because A star is also compact, but in fact, they have the same dimension. Beautiful. So it gives us more information on these operators A lambdas. Proof. So, following the above discussion, we can assume R is equal to 1. Okay, so we don't have to worry about. Okay. Set as notation, set N1 lambda to be the null space of A lambda, and N1 star lambda to be the null space of A lambda star, just for notation. Since they are both finite dimensional, set N to be the dimension of N1, and M to be the dimension of N1 star of lambda. Okay, so we want to prove, let us prove N equals to N. Okay, first, if one of them is equal to 0, so if M equal to 0, we get in my note I called, so I don't want to do some mistakes down the road, let's call this one M and this one N. Okay, first assume M is equal to 0, then the null space N1 lambda is reduced to 0. Okay, so which means, remember, the S and the R that's associated to the spaces of A lambda n's, it means that the first one, N0 and N1 are the same, and therefore, so X is going to be the direct sum of R of A lambda plus N of A lambda. Okay, which is R1 of lambda. Okay, because N1 lambda is equal to 0, but N1 star of lambda, or A lambda star, and the null space of A lambda star is the R of A lambda orthogonal, which is 0. So A lambda star is injective, okay, injective, okay, among other things. Okay. And in particular, this implies that so the dimension of N1 star is equal to 0, or N is equal to 0. N is equal to 0. Okay? Now assume N equal to 0. So in this case, same argument, X star is going to be equal to N1 star lambda plus R1 star lambda. Okay? Same argument. So this will give us what? So X star is equal to R1 star lambda, which means that A star lambda is surjective. So but N1 is going to be R star lambda orthogonal, or N1, because it's equal to X star, so the orthogonal, when you go back to X, you get 0, which implies N equals 0. Okay? Okay. So obviously, n and m, if one of them is equal to 0, the other one is equal to 0. So now, assume n and m are greater or equal than 1, okay? And let us prove that they are equal. So here, set n1, okay? Set n1 lambda equal the span of x1, x2, xm, because m was its dimension, n1 star lambda equal the span of x1 star, x2 star, all the way to xn star. Okay. Since they are bases, so x1 star is not 0, there exists e1 in x such that x1 star of e1 equals to 1. Okay? So now let us build a sequence of ei's in x such that they behave like what we call a bioorthogonal basis to xi star. Let me explain exactly what. So we do it by induction. Assume that e1, ek are found such that xi star of ej is equal 0 if I is different from j, and 1 if I is equal to j, and this is for I and j between 1 and k. Okay? So here, for k less than n. So you start with 1, the first one is done, and then you start building them, okay? So now let me show you how to build the next one, ek plus 1, okay? So here, so assume for any x in x that whenever the first ones are equal to 0, this lemma, by the way, we have seen it. It's very powerful. It's called the Ritz lemma. So we have used it before when we showed that the norms in a finite dimensional space are all equivalent. So it's a beautiful lemma, and I'm just using it. I'm going to use it right here, okay, to prove the existence of the EIs. So assume that for any x, whenever the xi star are equal to 0, then xk plus 1 is equal to 0. Assume that, So for any x, xi star x equals 0, for I equals 1 all the way to k, then xk plus 1 star of x equals to 0. If that's the case, we know from the Ritz lemma that xk plus 1 is a linear combination, okay, of x1 star, xk star. But this is not possible because we are talking about a basis of n1 star, so this is not possible. So what does it mean? It means that there exists an x belongs to x such that, okay, xi star of x are all equal to 0, from I equal 1 all the way to k, but xk plus 1 star of x is not equal to 0. Okay? So you divide by this number and set ek plus 1 to be this x divided by xk plus 1 star of x. Okay? And this tells us that xi star of ek plus 1 equals 0 for I equal 1 all the way to k, and xk plus 1 star of ek plus 1 is equal to 1. Alright? So by induction, we get that okay, remember, so we have this xi stars all the way to en. So e1 all the way to en, okay, exists in X such that, this is very important, such that whenever you have a linearly independent family of vectors in X star, you can always build through this lemma, this sequence of vectors. Sometimes we call them the biorthogonal ones, okay? Such that xi star of ej is equal to 0 if e different from j, and 1 if a is equal to j, and this is for I and j between 1 and n. You can also use the canonical symbol delta and write here delta of I, j, and delta ij is exactly what it is, 0 if I is different from j, and 1 if I is equal to j. Okay, so we have now this sequence of vectors in X associated to the xi stars. Okay, they are linearly independent. Okay, so they are linearly independent. E1, En are linearly independent. It's a piece of, I mean, it's not like hard. Linearly independent. Childish proof. Indeed, if sigma of alpha I ei 1 to n equal to the 0 vector, then if you take xi star of sigma of alpha j ei I from 1 to n equal to 0, this is exactly alpha j for any j. So this tells us, so alpha 1 equals alpha 2 equals alpha n equals to 0. So you are now in X, and you have a linearly independent what? Family. Okay? Great. Same proof, same idea will help us prove the existence of another family, existence of E1 star, En, Em star in X star, such that Ei star of xj, same, equal 0 if I is different from j, and 1 if I is equal to j, and this is I and j between 1 and n. Okay? Same thing. So next, okay, introduce an operator, new operator, okay, b, set b to be a of x, sorry, let's put x here, b of x equal a of x plus sigma of ei star of x, xi, and this is from 1 to n. Okay? And of course, I'm going to be assuming that m is less than n. Okay, so first assume m less than n, and introduce this operator. So this part is compact, and this part is compact because you are in a finite dimensional space. Therefore, the sum of two compact operators is compact. So B is compact. Okay, and also we have lambda I minus B, okay, of x is equal lambda I minus A of x minus sigma ei star of x xi from 1 to n. Okay, so now what happens if x belongs to, n of lambda I minus b? Okay, then we have so then we have xj star of a lambda of x minus sigma of ei star of x xj star of xi is equal to 0, because lambda I minus b of x equal to 0, then we get this, right? Okay, great. So, but remember that xj stars, they span n1 star, okay, and therefore a xj star of a lambda x is going to be a lambda I star of xj, and that's 0, okay? So this here, this part, so this right here, since xj star of a lambda x, this is a lambda star of xj star of x, but this vector here is 0 because they belong to the null space of a lambda star. Okay, the xj, they span it. So this will be equals to 0. Okay, and also by definitions, so this will apply we did a little tiny mistake here. This x, in fact, is ei. Okay, so this here is ei, and this one here is ei. Okay, and because I want to use the relationship between the xj star and the ei's, so this would apply. So minus ej star of x is equal to 0. Okay, so in particular, this is true for any j. Okay, for any j from 1 to m. So this tells you that for any j between 1 and n, okay, that was true. So this tells us that lambda I minus b at x equal 0 equal a lambda of x minus 0. Okay, because they are all the I stars are equal to 0. So a lambda of x equals 0, or x belongs to n1 of lambda. Okay, excellent. So this implies, so the null space of lambda I minus b is in the null space of lambda I minus a, or n1 lambda. Okay, so let x belongs to n of lambda I minus b, then x is in the span of the xi's, so this will be sigma of alpha I xi from 1 to n. Okay, but we just proved that ej star of x is equal to 0 for j between 1 and m. Okay, and ej star of xi is equal to delta ij, okay? So alpha i's are all equal to 0 for 1 to n, or x is equal to 0. So this null space of lambda I minus b, so the null space of lambda I minus b, in fact, is 0. Okay? So we do have lambda I minus b, okay? Inverse. So lambda I minus b inverse exists from the range of lambda I minus b, which is closed because b is compact, into x. So keep in mind that the range is closed, so we can go from the range into x. Okay? In particular, we have the range, it is equal to x, okay? Now, since m is less than n, then n plus 1 is less or equal to what? To n. So there exists x in x such that lambda I minus b of x is equal to en plus 1, okay? But en plus 1 star of en, okay? Sorry, it's not e, it's x star. Okay, it's equal to 1, and x star n plus 1 of en plus 1 is equal, now we use the fact that it's lambda I minus b of x, and that's a lambda, sorry, x star n plus 1 of a lambda x minus sigma of ei star of x, x star n plus 1 of ei, I from 1 to n. So now what happened is that this one, again, is equal to 0, because that's just a lambda star of xm star, and they are the spanning of the null space of a star. And this one, by definition, they're all equal to 0, so we get that this is equal to 0, which is a contradiction. So on one hand we have 1, on the other hand we have 0, so this tells us what? Contradiction. Okay. So n is less or equal than n. Okay? Next, assume we do the same, exactly the same, but by duality. Assume that n is less than n, and we introduce a new operator. Okay? Set C that goes by duality here. Okay? And we repeat the same process. Okay? C defined by C of x star equals a star x star plus sigma of x star ei times xi star I from 1 to n, and use the fact that C is going to be compact, and then do the same, exactly the same proof to show that this will lead to a contradiction. This will lead to a contradiction. Similar, exactly as we did before. Okay, therefore we must have n equal to aim as claimed. Hope you enjoyed this lecture. It was a long one on adjoint operators with so many properties and of the adjoint operator. Thank you very much, and see you in another lecture.